Hello everyone, my name is Huziel Sauceda from the Instituto de Física at UNAM in Mexico City. Today I will talk about dynamical strengthening of covalent and noncovalent molecular interactions induced by nuclear quantum effects. This work was done in collaboration with the group of Professor Kachenko and Professor Müller. The study of nuclear quantum effects consists in substituting the classical nuclei by its quantum counterpart. And by doing simulations within this approach, we can recover very interesting statistical properties regarding, for example, population analysis, spectroscopy, as well as some proton diffusivity. But most of the works done up to now in this field have focused on the mechanical implications and the potential energy surface sampling. So in this work, what we do is to go in a different direction, and we try to correlate the nuclear quantum effects and the covalent and non-covalent interactions, and we will find out that the nuclear quantum effects actually strengthen certain type of interactions in molecular systems as well as in materials. Well, to study this, we will use the nuclear quantum, the path integral formalism, which includes these nuclear quantum effects in the system. To describe the forces in the interatomic forces, we will use the gradient domain machine learning framework. In particular, we will use the symmetric GDML as well as the Bravais-inspired GDML for materials. In order to evidence these properties or these implications, we will choose these two types of systems, which is on one side the aspirin, on the other side the benzene dimer. Well, within the aspirin case, we want to study how the system explores the energy landscape. And first, we did a couple of years ago, we performed some simulations room temperature with a SEDML model trained on coupled clusters, single and double forces. And we obtained actually that the system is quite free, explores the potential in the configurational space. And here we show it via the projections to the two main degrees of freedom of the system, which is the dihedral angles of the ester and the hydroxyl groups. But we noticed that when we turn on the nuclear quantum effects, suddenly the system localizes and around the global minima of the system. So in order to understand what was going on here, we decided to first investigate what is the main contribution to the energy to the global minima stabilization, and it's actually an electronic transition which consists in the electron lone pairs in one of the oxygen atoms. They move into the unoccupied orbital in the ester group, where the main degree of freedom of this interaction is the distance between the oxygen and the carbon atoms. So with this in mind, we perform a statistical analysis. We subsample all these regions, and then we computed the transition energy. As a result, and first as a reference, we computed the contribution of this N2 pi asterisk energy, and we found that when we turn on just by putting temperature in this phenomenon, this interaction increases already. But when we turn on the nuclear quantum effects, what we see is that the highest value of this interaction is actually quite high compared to the classical MD, and is actually 1.7, approximately 1.7 times the energy from the classical system. So from this, we can actually conclude that the nuclear quantum effects strengthen this N2 pi asterisk interaction, and by doing so, this causes that the system localizes around the global minima, and in other words, it causes this configurational localization. Okay, now we move into the case of the implications on dispersion interactions and in non-covalent interactions. Before going into the results, we first analyze the system. We know that the attraction interactions for this kind of system can be described for using an r to the minus 6 potential. And from this, we know that the strength of the interaction is given by the C6 coefficient. But at the same time, this C6 coefficient depends on the polarizability of each one of the fragments. But we also know that this polarizability is proportional to the volume of the electronic clouds to some power, which recently was demonstrated, that is 7/3. But what this analysis tells us is that the interaction strength of between two fragments is proportional to the volume, meaning that if we dilate artificially the volume of each one of the system of the parts of the system, the attraction force will increase, and this leads us to think about the possibility of some thermal dilation of the system. But more interestingly, we introduced the concept of this nuclear quantum interatomic dilation, meaning that just by the inclusion of the 0-point energy in our simulations, the system will tend to dilate, which then will mean that the attraction force between different fragments will increase. And to analyze this kind of phenomena, we focus on the benzene dimer. Okay, these are the well-known curves for this system. But then here we know that it is well known that at 0 Kelvin, these two configurations, the parallel displaced and the T-shaped, are the generating energy. But here we decided then to include some thermal fluctuations. Actually, these are simulations at room temperature. And then we can see that the effective free energy here breaks a bit the degeneracy between the two configurations. But what happens if we include the nuclear quantum effects? Well, in the case of the parallel system, of the parallel configuration, we have an increase of 20% in attraction energy. While in the case of the T-shape, we have merely a 2% increment of the attraction energy. But in the case of the parallel displaced, we obtain an 11% increment just by including thermal and nuclear quantum effects. This means that a real system and experiment, the actual energy of these two configurations is not degenerate, and in particular, the parallel displaced will be favored and should be measurable in an experiment by the statistical occupation of each one of the configurations. And following the same idea, we can analyze the interaction of the benzene molecule with graphene. And here we did actually artificially, we inflated or we dilated the benzene molecule, and we see that as soon as we are changing the effective area of the benzene molecule, we obtain this linear dependence of the increment of the van der Waals interaction between the two systems. But then we move to performing actually classical molecular dynamics of the system, plotting here we have the relative angle to the plane. And here we see that the system, well, it fluctuates a lot, and it flaps, and because it explores a wide variety of values of the angle. But as soon as we turn on the nuclear quantum effects, the system immediately localizes. And this is because, indeed, this nuclear quantum dilation in the benzene molecule strengthened the interaction, dispersion interactions between the graphene and the molecule. Well, just to summarize, we found out that by including nuclear quantum effects, this enhances the intra-molecular interactions, but as well as non-bonded molecular interactions. And just to explain a bit of what we meant by dynamical strengthening, well, we found that these nuclear quantum effects, they induce a structural rearrangement of the system, and then at the same time, this changes the way the atoms interact, and then this again produces a structural arrangement, and this back and forth between these two type of phenomena is fed by thermal fluctuations, and then this produces a synergy in the dynamics of the system. And with this, we have shown some evidence that indeed nuclear quantum effects, they enhance inter and intramolecular interactions. Thank you.